Let's go! Chapter 8, lesson number 8, points of inflection. Woo! An old favourite from higher, that is where we were first introduced to points of inflection, but this year we want to take it a little bit further and look more at points of inflection. So first of all, what is a point of inflection? Well, that is a point at which a curve changes from being concave down to concave up, or vice versa. Concave down and concave up were terms that we were introduced to in the last lesson. Remember, concave down means that the gradient is decreasing from left to right. So if you have a curve here, you can see that if we take the gradient at, say, that point there, I'll just draw in the tangent so it's easy to see. And then if you take a bit further along and draw in the tangent, well, you can see the gradient has decreased. If you take another point there, again, the gradient just keeps on decreasing. Or a point here, again the gradient is decreased. So you can see that from left to right the gradient has decreased, and that is what's meant by concave down. Concave up is when the gradient is increasing. So if we're starting off with just a point here, imagine if you drew in a tangent so you can easily see the gradient. Well, if you pick a point later on, draw in the tangent, well, you can see that it is increasing. So the gradient's increasing, so that there is known as concave up. So a point of inflection is where the curve changes from concave down to concave up, or vice versa. In other words, it's where the gradient changes from decreasing to increasing, or vice versa. Really, in higher, all the points of inflection that we looked at were stationary points. If you remember, you had your point of inflection, it looked something like that. That was your stationary point where the gradient was 0. And really, you had your gradient decreasing. So the gradient is very, very steep, and then it's decreasing, decreasing, decreasing. It gets to 0, and then it starts to increase again. This point here is your stationary point, and because your gradient changes from decreasing to increasing, it's a point of inflection. You could have it the other way around as well, hopefully drawn better than that, but you can see that the gradient starts to kind of level off. The gradient is increasing until it gets to 0, and then after that the gradient starts to decrease. So the gradient is increasing, then it's decreasing. Because it changes from increasing to decreasing, it's a point of inflection, and that obviously is a stationary point. That's what we're looking at in higher. However, that doesn't always have to be the case. If you look at this funky wee graph here, you can see that the gradient, imagine if you started up here going from left to right, well, the gradient is very, very steep there, but again it starts to level off, so the gradient is increasing. So the gradient is increasing going from left to right, it gets to 0, and then it starts to increase even more. However, there is a point, this point here, that's known as the inflection point, where it stops increasing and it starts to decrease. And it starts to decrease until it gets back down to 0, and then it keeps on decreasing. So again, you're looking at it, you're thinking, right, well, if you took the gradient at that point, if we drew in the tangent there, if we took another point there, well, we can see that the gradient here will be higher than the gradient there. Again, the gradient here will be higher, so the gradient is increasing from left to right. Just at that point, though, instead of increasing, the gradient starts to decrease. So because it goes from increasing to decreasing, that there is also a point of inflection. At the exact point when the curvature changes sign, so the gradient changes from increasing to decreasing, really the gradient, the rate of change of the gradient is neither positive nor negative. And therefore, well, from last lesson we were looking at the second derivative, and if the second derivative equals 0, then it indicates there could be a possible point of inflection. I'm saying a possible point of inflection because just because the second derivative equals 0, it doesn't always indicate a point of inflection. It could still be a maximum or minimum. So more tests, more checks will have to be done. You'll have to look at the concavity, check for a change of sign. Really then, if a point of inflection occurs at a stationary point, then it is known as a horizontal or stationary point of inflection. And really, these were the ones that we looked at last year. The tangent at the point really is horizontal. The first derivative was equal to 0. And as I said, if I just draw a tiny wee diagram here, you can see there the gradient 0. That there is your point of inflection. The gradient is changing from decreasing to increasing. It's a point of inflection, and it's a stationary point. So it's known as a stationary point of inflection. However, if the point of inflection does not occur at a stationary point, it is known as a non-horizontal or non-stationary point of inflection. And this is where the tangent at that point is not going to be horizontal. In other words, the first derivative is not equal to 0. Remember, the first derivative, stationary points occur when dy by dx equals 0 or f dash x equals 0. If it's not equal to 0, then it will be a non-stationary point of inflection. That is shown just with these diagrams here. So for this one, this is what we were dealing with last year. There is your stationary point. That's a stationary point. The curve, the gradient is changing from decreasing. The gradient is still decreasing, decreasing, decreasing. It gets to 0. And then the gradient starts to increase once again until it's pretty steep. So because the gradient's changing from decreasing to increasing, that is known as a point of inflection, and because there is a stationary point, it's a stationary point of inflection or horizontal point of inflection, because the gradient there would just be 0. So the gradient, the tangent, is 0. With these two examples, you can see that for them, well, they are still points of inflection, because once again the gradient is decreasing and then decreasing. It gets to 0 and it keeps on decreasing, but just at this point it then starts to increase. And because the gradient changes from decreasing to increasing, that is also a point of inflection. It's just not one of the ones we dealt with last year. It's not one of these. Gradient changes from decreasing to increasing, so it's a point of inflection, but it's a non-horizontal or non-stationary point of inflection. And it's the exact same here as well. That is clearly not a stationary point, and the gradient, you see, it starts to decrease. It's decreasing a bit more, but then suddenly, instead of continuing just to decrease and come around like this, it starts to increase once again. So that is also a point of inflection, and it's a non-stationary point of inflection. Let's look at some examples. Example 1, find any points of inflection on the graph of f of x equals 5x cubed plus 8x. So we know that at a possible point of inflection, the second derivative equals 0. So we're wanting to get the second derivative here. So f of x equals 5x cubed plus 8x. The first derivative, f dash x, will be, you got it, 15x squared plus 8. The second derivative will be, you still got it, so it will be 30x. At a possible point of inflection, the second derivative equals 0, so set that equal to 0, so 30x equals 0. If 30x equals 0, then x clearly equals 0. Let's get the y value as well while we're here. So when x equals 0, sub that into f of x. So f of 0 will equal 5 times 0 cubed plus 8 times 0, which just gives you 0. So you know the x value is 0, the y value would be 0, so there is a possible point of inflection at 0, 0. Dun dun dun! A possible point of inflection. Why am I saying a possible point of inflection? Well, just remember that just because that second derivative equals 0, it doesn't necessarily mean it has to be a point of inflection. It could still be a maximum or a minimum. So let's test for that, and the way we test for it is to test the concavity. But before that, let's test if it's a stationary point, because if we find it's a stationary point, then it could be a maximum or a minimum or a point of inflection. So is it a stationary point? Let's look at that. We already know that f dash x equals the 15x squared plus 8, and we know that x was equal to 0 for that second derivative. So when x equals 0, if you sub that in, well, f dash 0 equals 15 times 0 squared plus 8, which is equal to 8. And because it's equal to 8, because the first derivative equals 8, then it means that that first derivative is not equal to 0 when x equals 0. And because it is not equal to 0, then it means that the point 0, 0 is not a stationary point. So it's not a stationary point, so it cannot be a maximum or a minimum. But it could still be a point of inflection, and the way we test for that is to test the concavity. So remember, we had the second derivative, f double dash x equals 30x. And what we do with that is we put it into something that's very like a nature table. So we take our value that we found, we had x equals 0, and we take a value just before and just after that, go out by 1 decimal place. We want to sub them into the second derivative. So if you sub in negative 0.1 in place of x in 30x into the second derivative, you end up with a negative. And because you get a negative, it shows you that the gradient at negative 0.1 is decreasing. So because the gradient is decreasing, that would be concave down. Remember, the gradient is decreasing, it's concave down. A point of inflection occurs when the gradient changes from decreasing to increasing or vice versa. So what we're hoping for is that just after this point that we will have something that is going to be concave up, because then the gradient would change from decreasing to increasing. If you sub 0 in, we're obviously getting 0. That doesn't really tell us anything. But if we sub in 0.1, we would have 30 times 0.1. That is obviously positive. And because it's positive, it means the gradient is going to be increasing. It's going to be concave up. So we can see here that the gradient would change from decreasing to suddenly increasing. And because of that, there is a change of concavity at that point 0, 0. And because there is a change of concavity, it means that 0, 0 is going to be a point of inflection. And because that first derivative was not equal to 0, it indicates a non-horizontal or non-stationary point of inflection. Yeah. Example 2, find any points of inflection on the graph of y equals x cubed plus 8 over 2x. Once again, you're thinking, for a possible point of inflection, d2y by dx squared equals 0. And you're perfectly right. So you have to find that second derivative. So we're starting off with y equals the x cubed plus 8 over 2x. Let's rewrite that before we differentiate. So we end up with a half x squared plus 4x to the negative 1. Differentiate that and we end up with x take away 4x to the power of negative 2. And for the second derivative, differentiate that as well. You end up with, perfect, 1 plus 8x to the power of negative 3. Just remember, at a possible point of inflection, the second derivative equals 0. So set that equal to 0. All I'm doing is moving the x cubed down to the bottom below the 8. So I've got the 1 plus the 8 over x cubed equals 0. Subtract 1 from both sides, so 8 over x cubed equals negative 1. Multiply both sides by x cubed would give you 8 equals negative x cubed. And if you multiply both sides by negative 1, you get x cubed equals negative 8. What number do you cube to get negative 8? Brilliant, you get negative 2. So negative 2 cubed would give you negative 8. So x would equal negative 2. Once again, if it's asking for a point, let's get the y value as well. So when x is negative 2, let's sub that into y equals the x cubed plus 8 over 2x. And we end up getting, what do you get? 0. Perfect, you end up getting 0. Which means then that there is a possible point of inflection at negative 2, 0. Once again, I'm saying a possible point of inflection. Just because that second derivative is equal to 0, it doesn't necessarily mean it is going to be a point of inflection. It could also be a maximum or a minimum, and you need to test the concavity. Just before we do that though, let's test if it's a stationary point. So, for the stationary point, we've got dy by dx equals x take away 4x to the power of negative 2, and we know the x value was negative 2. So if we sub that in and we get 0, then we know it is a stationary point. So it could be a maximum, a minimum, or a point of inflection. If we don't get 0, then it can't be a maximum, it can't be a minimum, but it could still be a point of inflection, and that's where you would do your concavity test. So when x equals negative 2, sub that into dy by dx. That would give you negative 2 take away 4 times negative 2 to the power of negative 2. I'd probably move that down to the bottom, so I'd have 4 over negative 2 squared. Work that out, and you end up getting negative 3. Since that first derivative, dy by dx, is not equal to 0, Wah, wah, wah. It means then that negative 2, 0 is not going to be a stationary point. So it is not going to be a maximum and it's not going to be a minimum. But it could still be a point of inflection, and we have to test the concavity. So to do that, you are using the second derivative. That second derivative was 1 plus 8x to the power of negative 3. Remember, you are using something similar to your nature table. So you're taking x, you've got negative 2, pick a value just before that, go out by 1 decimal place to give you negative 2.1, and a value just after with negative 1.9. Sub these values into that second derivative. So if you sub in negative 2.1 into 1 plus 8x to the power of negative 3, you end up getting a positive value. Woo! Because it's a positive value, well, the gradient is going to be increasing. And when it's increasing, it's going to be concave up. So you can see here, the gradient is increasing. When you sub in negative 2, just check that you do get 0. But sub in the value after that as well, sub in the negative 1.9. So 1 plus 8 times negative 1.9 to the power of negative 3, or just rewrite that, work it out. Is it positive? Is it negative? It is negative. And because it's negative, it means the gradient is going to be decreasing. So a negative, it'll be decreasing there. So it's going to be concave down. Just remember, at a point of inflection, the gradient changes from increasing to decreasing, or vice versa. And you can see here it is changing from increasing, concave up, to decreasing, concave down. So there is a change of concavity at that point, negative 2, 0. So you can say that negative 2, 0 is a, and because up here it is not a stationary point, the first derivative is not equal to 0, it means it is a non-horizontal or non-stationary point of inflection. Yeah! Example 3. Find any points of inflection on the graph of y equals x to the power of 6. Take away 1. Once again, you know that at a possible point of inflection, that second derivative, d2y by dx squared, equals 0. So differentiate. You have y equals x to the power of 6, take away 1. dy by dx will equal 6x to the power of 5. And the second derivative works out to be 30x to the power of 4. At a possible point of inflection, that second derivative is equal to 0, so set that equal to 0. You can easily work out that x must be equal to, you got it, x equals 0, divide both sides by 30, take the fourth root. X is going to be 0. When x equals 0, let's just work out the y value as well. So when x is 0, sub 0 in place of x. So y would equal 0 to the power of 6, take away 1, which is obviously negative 1. Therefore, there is a possible point of inflection at 0, negative 1. So now we need to test that. So we've got this possible point of inflection. Let's first of all think, is there at a stationary point when x equals 0? If it is, then it could also be a maximum or a minimum as well as a point of inflection. So let's think about the stationary point. dy by dx was equal to 6x to the power of 5. When x was equal to 0, what is dy by dx equal to? Well, dy by dx would equal 6 times 0 to the power of 5, which equals 0. Bum, bum, bum! That means then that dy by dx, if it equals 0, that 0, negative 1, or point is a stationary point. So it could be, dun, 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 it could be a maximum, or it could be a minimum, or it could be a point of inflection. Remember, just because the second derivative equals 0 doesn't make it a point of inflection. It could be a maximum or a minimum as well. And the way we have to test for that is by using the nature table. So the nature table, just the one that you've been using from higher, you've got the value of x. X was equal to 0, pick a value just before that and just after, sub that into the first derivative to work out the gradient. So if you sub in a value just before 0 into dy by dx, in other words, sub in a negative, well, it's quite clear you're going to get a negative, which means then the graph will be sloping down the way. After that, you've got 0, sub that in just to double check it. Well, yes, you do get 0, so the gradient is 0, it's going to be flat. And after that, if you sub in a value bigger than 0, Well, if you sub n say 1, then you are going to get a positive value. That means then that your graph is going to be going down, then it's going to be going up, and because of that, well, you can clearly see that it is not a point of inflection, it is going to be a minimum turning point. So you get the minimum turning point there, but also when we set that second derivative equal to 0, the only value we found for x was 0. So it means then that on that curve, there are no points of inflection. The only thing that we came up with was a minimum turning point. Try these questions in the Unit 2 booklet, page 53. Check your answers as you go. Best of luck trying to find points of inflection and determining whether or not they are stationary points of inflection. Have fun. See ya.